So this is a short video about gas calculations. Hopefully you've already seen the video about gas calculations where 1 mole of gas occupies 24 decimeters cubed, as long as you're at room temperature and pressure. And also in that video we looked at comparing volumes of gases in equations. So as long as you're at the same temperature and pressure, you can use this stoichiometric ratio with volumes as well. In this video, we're going to look briefly at the ideal gas equation and then looking at an equation where P1 V1 over T1 equals P2 V2 over T2. We'll start with the ideal gas equation. So there are lots of different laws about gases and how pressure and volume and temperature are related. You already know quite a bit about gases from everyday life. So if you have a balloon and you put it in a freezer, it will get smaller. If you heat that same balloon up, that balloon will get larger. If the balloon is fixed and can't expand anymore, but you keep heating it, the pressure will go up and eventually it will pop. So there are lots of individual laws about gases which we don't have to know, but they're combined to something called the ideal gas equation. And this you do need to memorize. Most people don't have any problems remembering this one. So it's PV equals nRT. You need to know what each of those quantities are and importantly what units they have. So P, unsurprisingly, is pressure. And for this equation to work, pressure must be in pascals. So any sums will only work if pressure is in pascals. V is for volume, which you might expect, and it's the units for volume that often catch people out. If you think about a gas, 1 centimetre cubed of gas is a tiny amount of gas. That's really not very sensible. 1 decimetre cubed is often suggested by people, but remember a decimetre cubed is about a litre. And again, a litre of gas isn't really very sensible. So volume here has to be in meters cubed. So we have to be dealing on the scale of meters cubed. If you have a value in centimeters cubed, that's, if we think about it, 1 by 1 by 1 by 1, so just 1 centimetre cubed, to get up to a metre cubed. If you think about what you learnt about a metre at school, a metre is 100 centimetres cubed, or 100 centimetres. So a cubic metre would be 100 by 100 by 100. And if you work that out, that actually comes out as a million. Okay, so the conversion between centimetres cubed and metres cubed is a million. If I've got my value in centimetres cubed, that means I don't have many metres cubed. So I need to make my number smaller. So I would need to divide by 1 million. If I've got my value in metres cubed, that means I'm going to have lots of centimetres cubed, so I need to make my number bigger and I need to multiply by a million. In the middle, we've got decimeters cubed, and we already know from doing titration calculations that if you have a value in centimetres cubed and you want to get it into decimeters cubed, you would divide it by 1,000. And so decimeters cubed to meters cubed is another divide by 1,000. If I want to go the other way, I would need to times by 1,000 to get from meters cubed to decimeters cubed, and then times by 1,000 to get from decimeters cubed to centimeters cubed. So this is a really key thing to remember. That, believe it or not, is actually where most people go wrong in these calculations. So that's P and V. N is number of moles. So N is number of moles. R is something called the gas constant. And as the name suggests, this is a constant. The value is always the same. The value can be found on your data sheet. So it's on the front of your data sheet. You don't need to memorize it. It's 8.314 joules per mole per Kelvin. So that gives us a clue about the last quantity, which is T, which must be temperature. And you can see, because of the gas constant, that this must be in Kelvin. And most people hopefully can get from degrees C to Kelvin. So if you have 0 degrees C, that is 273 Kelvin. So Kelvin is what we call the SI unit for temperature. That's the official scientific unit for temperature that we should use. So if you want to work out your temperature in Kelvin, you add 273 to whatever your value is in degrees C. So we've got this equation which links pressure, volume, number of moles and temperature. We can see a couple of things just by looking at it. Pressure and temperature, for example, are on different sides of the equation. That means they are proportional to each other. So if pressure goes up, then temperature must go up. Same for pressure and number of moles. So if you suddenly add more moles of gas, but you keep the volume constant, then your pressure would go up. Whereas if you've got two quantities on the same side of the equation, they are inversely proportional to each other. So if I keep my number of moles and my temperature constant, if pressure goes up, the way I would do that is by making volume go down. So that's just quite a handy thing to be able to do. But most often we just use the ideal gas equation for calculations. And these would be calculations where we are not at 25 degrees C and 1 atmosphere pressure. If we are at 25 degrees C and 1 atmosphere pressure, we would simply use the fact that 1 mole of gas occupies 24 decimeters cubed. If that's not the case, we have to use the ideal gas equation. So, for example, we might have a question where we're told that that a sample of gas occupies a volume of 590 centimeters cubed at a temperature of 120 degrees C and 202 kilopascals. And we're asked to calculate how many moles of that gas we have. So if we've got a question like this, it's a good idea to look at all the terms in the ideal gas equation and make sure that if we have the numbers for those terms, that they're in the correct units. So we've got pressure at the moment in kilopascals, but for the ideal gas equation it has to be in pascals. So I'm going to times it by 1,000. So if you think kilopascals to pascals is similar to kilometers to meters or kilojoules to joules. So times it by 1,000, and then I got 2.02 times 10 to the 5 pascals. If I've got kilopascals, that means I have lots of pascals. My volume at the moment, I've got in centimeters cubed. And remember, I need it in meters cubed, and this is probably where most people go wrong. And if I've got 590 centimeters cubed, I don't have many meters cubed, so I need to make that number smaller. So I'm going to divide it by 1,000,000, and that gets me to 5.90 times 10 to the minus 4 meters cubed. N is my number of moles, and that's what I'm trying to find. R, remember, you can find on the data sheet, you can look up, it's a constant. And then T, at the moment I've got it in degrees C and I need it in Kelvin. So I add 273 to that and I get 393 Kelvin. Once I've done that, I think about my ideal gas equation, PV equals nRT. I am trying to find the number of moles, so I need to rearrange it. This is where you need to be okay at rearranging simple equations. So I've got a times R times T. To get rid of them from this side, I
divide both sides by R and T. Then we simply substitute our numbers in carefully. And when you're doing an exam question, it's really important that you write out these steps so the examiner can see what you've done. So in case you accidentally put any numbers into your calculator incorrectly, they can see what you've done and you can have error carried forward marks. Okay, so 8.314 times 393 is on the bottom. And when you put that into your calculator, you should find you get 0.0365 moles. So just be very careful how you put this into your calculator. You might need lots of brackets. Particularly be careful with how you do times 10 to the something. People sometimes press the wrong button on their calculator. You're looking for, often there's a button that says EXP. That's the button that you want. So just be careful. As I said, you might also want to do lots of brackets, or you can always work out the top number, then work out the bottom number and do the division afterwards. So just be careful. So for this example in itself, it's not a complicated calculation. It's just about being careful with your unit conversions and then careful with how you enter it into your calculator.
So you might get asked a slightly different question, a variation on this. So in this question, we're told that 1 decimeter cubed of gas at 0 degrees C and 1.01 times 10 to the 5 pascals is found to weigh 1.25 grams, and we're asked to calculate the molar mass of the gas. So remember, molar mass is the mass of 1 mole, and that is literally just the MR. So we're being asked to calculate the MR here. So if I was doing this question, I would spot that it was about gases. So I think, right, I need to do a calculation about gases. I've got a temperature, and I've got a pressure, and I've got a volume. So then that makes me think, okay, I need to use the ideal gas equation. So PV equals nRT. So I sort of start thinking about, what do I know? I know R because it's a constant. I know T because I'm given my temperature. I'm given a pressure and I'm given a volume. That allows me to find the number of moles. The question asks me to find the molar mass, which is the MR. So if I remember, we learned earlier that moles is mass over the MR. So I have my mass, I'm going to calculate moles, so therefore I can rearrange to find the MR. Just like the previous question, the main thing here is to check that you've got all the numbers in the correct unit. So pressure I want in pascals, it's already in pascals. My volume, I have it in decimeters cubed and I want it in meters cubed. So I need to divide it by 1,000. So I get 1 times 10 to the minus 3 meters cubed. Number of moles is what I'm trying to find. R is my constant, so I can check my data sheet. My temperature is 0 degrees C. I need to convert it to Kelvin by adding 273. So I simply have 273 Kelvin. So I can rearrange my ideal gas equation and I find that N is equal to PV over RT. So in this case, I would have my pressure multiplied by my volume over the gas constant multiplied by my temperature. And as I said, just be careful putting this into your calculator. You might want to work out each kind of half separately and then do the division. And here we find that that is 0.0445 moles. So we know moles is mass over mR, therefore mR must be my mass over my moles. So my molar mass, my mR, is my mass of 1.25 grams over the number of moles that I found, and that gives me 28.1 as my mR. The official units of mR and molar mass are grams per mole. So you can see questions like that. Often you can do experiments similar to this. So for example, you might have a liquid and you might weigh the liquid, and then if you heat it, you can turn it into a gas and measure the temperature, the pressure and the volume and do that. So lots of similar calculations and experiments are based on this. Okay, so that's the ideal gas equation. Hopefully you've got the idea there. There are then a different type of calculation. So this we would do when we have a single sample of gas. So you're just sticking with the same sample of gas, but you are changing the conditions. So whether that be temperature, pressure, or volume. And essentially you can work out how you derive this equation. So you kind of add two ideal gas equations together. I'm not going to show you that, you don't have to know, but you end up with the equation P1 V1 over T1 is equal to P2 V2 over T2. Okay, so P1 V1 over T1 equals P2 V2 over T2. So this one kind of rolls off the tongue quite easily. And as hopefully you might expect, these are conditions 1, so they're your start conditions, and these are conditions 2, so those are your end conditions. And the really nice thing about this equation is that temperature must be in Kelvin, but, so we're kind of used to that, but pressure and volume can be any units, okay, as long as you're consistent. So you can't have pressure 1 in pascals and pressure 2 in atmospheres, that wouldn't work, but they could both be in atmospheres or they could both be in kilopascals, same for volume. So they could both be in centimetres cubed. So that makes these sums slightly easier. So an example of how we might do this. So our question might be, what temperature in degrees C is required to cause an ideal gas? Remember, we treat them all as if they're ideal gases. To occupy 1.34 decimeters cubed at a pressure of 2.05 atmospheres if it occupies 756 centimeters cubed at 1 atmosphere and 0 degrees C. Okay, so it's the same sample of gas. I'm just changing my conditions. So again, I would outline what numbers I need to put into my equations. So my start pressure is 1 atmosphere, and I can leave that in atmospheres. My start volume is 756 centimeters cubed. Now I've got 1 centimeters cubed and 1 decimeters cubed, so I have to make them both the same. We're most familiar with converting into decimeters cubed, so I'm going to do that. So I divide by 1,000 to get 0.756. My temperature, I've got it in degrees C. I need to convert it into Kelvin by adding 273. Okay, so those are my starting conditions. My end conditions, my end pressure is 2.05. My end volume, I want to be 1.34 decimeters cubed. My end temperature is what I'm trying to find out. So what temperature do I need to make it have this pressure and this volume? I can substitute my values in, so I've got P1V1 over T1 is equal to P2 V2 over T2. And so we just need to rearrange it to find T2. Now you can work out each bit separately. So sometimes I will work out this side, which then just gives me one number to work out, and then I find the rearrangement a bit easier, or you can do it all at once. So if you think about it, if I want to get rid of this divide by 275, I would times both sides by 275, and if I want to get rid of this divide by T2, I would multiply both sides by T2. So that gives us this. And then if I want T2 on its own, I've got these multiply values, and so I would divide by them. So you can put that carefully into your calculator, and you should find that that will give you a value of 992 for the temperature. And remember, that will come out in Kelvin, and check the question carefully. We want it in degrees C. So I would have to subtract 273 to give me my temperature, which is 719 degrees C. And there's my final answer. So not too tricky, you just have to be very careful.